might just take this off, just for now. All right. Hi, everyone. My name is Ayushi, and today I'll be talking about my research project about Bayesian mixture analysis. So, given a data set, how do I identify the characteristics of the data? Mixture analysis deals with identifying any clusters or subpopulations within the data, and from this we can infer the subcharacteristics. So just as an example on this graph here, we see that the data is actually a mixture of two normal distributions, which appears as a single mixed distribution. And in this data set here, we see that it has identified 4 different clusters within the data itself. So the likelihood of an observation Y being part of a certain subpopulation is given by the sum from 1 to k, where k is the total number of mixtures in the distribution, of the mixture weight times the distribution of the data. And in my case, for my analysis, I just chose to use a normal distribution, but otherwise you could use like a Poisson distribution or a multivariate or multinomial distribution. So the difference in approach between classical and Bayesian mixture analysis is the fact that the Bayesian approach uses reverse jump MCMC method, which is like normal MCMC, except the fact that there is a reversibility constraint on the moves, which allows for very efficient simulation of the posterior distribution, even if the parameters are unknown. And in my analysis, I chose to analyze the Bayesian finite mixture model with an unknown number of mixtures. So we know that there are n number of mixtures in the data, but we don't know how many, or what is n. And here's just a really brief pseudocode for the algorithm, but I don't have time for that right now, maybe later. So for my data analysis, I chose to analyze the Palmer penguins data set. On the x-axis here, we have the bill depth, and on the y-axis here, we have bill length. And these are just histograms of the data initially, what it looks like. So I used the R package mixak to be able to do my analysis, and in order to find the posterior distribution and associated statistics, I use this function nmixMCMC, which takes as parameters the data, a prior. I chose a uninformed uniform prior, the maximum number of components in the distribution, let's say 10, delta equals 1, that's for the mixture weighting, some parameters for the RJ MCMC and the MCMC. So we obtain a posterior distribution for k, the number of components, and for both chains in the MCMC simulation, we find that k equals 3 has the highest probability out of the other components, which tells us that our data set is likely to have k equals 3 components. And this is just plotting the obtained posterior distributions for the bill depth and the bill length for each of the chains. So here is the resulting predictive density for each of the axes, the bill depth and the bill length, and we see that for each of these axes, the algorithm has identified 2 distributions within the data. So two distributions for the bill depth and 2 distributions for the bill length. And that's the outcome for both of the MCMC chains. So this is a little bit of a busy figure, and I'll explain what's going on here. So in the background, we have a heat map showing where the darker regions show a higher density of data. And this is overlaid by a contour, which again shows that there's a higher density of data points in these regions, and we see that there are 3 distinct regions, which, going back to our obtained posterior density, we predicted that there was going to be 3 mixtures in the data, and we see that there are 3 mixtures in the data. And here what I've also done is overlaid the plot with the data points, and we see that there are 3 distinct populations which correspond to the species of penguins. And each of these have different characteristics. So the pink cluster, which is the adult penguins, have longer bill depths and short bill lengths. And same for the chinstrap penguins, which have long bill depths and long bill lengths. The gentoo penguins, on the other hand, have shorter bill depths and longer bill lengths. So mixture analysis, especially using the Bayesian approach, is very useful for identifying populations within the data. Thank you.
Thank you. Good first presentation. Any questions? Okay, I'll ask one then. Actually, when you showed your statistics for the chains, a few slides back.
Here?
Yes, here it looks like one, for chain 1, it's k equal to 1 has the highest probability.
Oh.
So actually it's interesting that your two
Right.
chains disagree rather widely.
Okay, I don't know, I didn't notice that, but you do have a point because I was analyzing the DIC of both of the chains, and yeah, we see that chain 2 has the lower DIC, which means that it's more like better or more statistically significant compared to chain 1. So yeah, I guess that is true that chain 2 fits the model better than chain 1 does.
So you think maybe they haven't quite converged? The chains are disagreeing.
Yeah, for this particular simulation, I guess the MCMC modeling for chain 2 happened to simulate the parameter space better than chain 1, which we do in fact see here. Like the pink line, which is chain 1, doesn't really fit the data very well, but chain 2, the green line, does give a better shape for the distributions.
How long were the chains?
For the purposes of compiling the report in R Markdown, I kept them pretty short, so 1,000, 2,000, but yeah.
And a more general question, so if I just use standard MCMC for this problem, is that okay? Or so is the only usefulness of reversible jump is that it somehow converges faster?
Yes. So you can use MCMC. Some Bayesian mixture analyses do use just normal MCMC, but yeah, reverse jump is better because it has the ability to efficiently simulate the posterior distribution even if the parameters are unknown, just because of the fact that it has a reversibility constraint on the moves.
Okay. No other questions?
Just for the so you assumed it was a mixture of two normals.
Mm-hmm.
Is that so? That's something you have to assume. It can be like a normal in a Poisson or something different.
Yeah, here. So yeah, for the Power Penguins data set, I just assumed like a normal,
Right.
but the literature has used things like Poisson or multinomial distributions.
And it could be a mixture.
It could be a mixture of either as well.
Okay.
So it's a very flexible model.
Yes.
Yeah, like it's a very flexible model which allows you to, learn about your data set in different manners.
Okay, thank you very much.
Thanks.
Thank you, Ayush.